This is AP Calculus AB. We're looking at the notes for 7.4 slope fields. Slope fields are a graphical representation of solutions to differential equations. A slope field is a pictorial representation of all the possible solutions to a given differential equation. Remember that a differential equation is the first derivative of a function, dy over dx. Thus, the solution to a differential equation would be the original function, f of x or y. There's an infinite number of solutions to the differential equation, dy over dx equals x minus 1. Show your work and explain why. If we separate our variables for this, and we're trying to find a general solution to this, we integrate both sides. The left side, if you integrate 1 with respect to y, you're going to get y, plus an arbitrary constant. We're just going to put that on the right side. If you integrate x minus 1 with respect to x, add 1 to the exponent, multiplied by the reciprocal, add 1 to the exponent, multiplied by the reciprocal, and then you add your arbitrary constant. You could add 1 to both sides, but once again, it's just one arbitrary constant. If you add it to another arbitrary constant, you get a third arbitrary constant. It's all arbitrary. This we call as a general solution. So show your work and explain why. Here's my explanation. F of x equals 1/2 x squared minus x plus c is a general solution of dy over dx equals x minus 1. And it represents all of the quadratic functions that could be f of x for dy over dx. Because depending on what c is, it's going to give you a different answer. And c could be an infinite number of numbers. It's an arbitrary constant. You might be wondering, well, for the AP exam, what are we going to be able to have to do with slope fields? Well, here are 4 things. It's my understanding, these 4 things. 1, if you're given a differential equation, sketch a slope field. It is tedious work. 2, given a slope field, draw a particular solution. 3, match a slope field to a differential equation. 4, match a slope field to a solution of a differential. So let's look at an actual slope field so we can get a better understanding of what's up. Given the differential equation below, compute the slope for each point, indicated on the grid to the right, then make a small mark that approximates the slope through the point. Now, as far as your scoring goes for this, all they care about is what happens on this graph. The work that you show off to the side, they could take it or leave it. That being said, I'm going to show you how I'm going to calculate these things. For example, I'm going to just do this randomly at first, and then I will show you sometimes there's some patterns that make things easier. For example, if we take the ordered pair right here, this ordered pair is -2, -3. So that means we want to put -2, -3 into this equation. And notice there's no place to put a y value, because it's just x minus 3. It's going to be -2 minus 1, which is -3. So that means the slope at -2, -3 is -3. Now, drawing that slope exactly through a point is difficult, but we know that it's negative and it's pretty steep. So I'll just do that. What about at -2, -2? It's this point right here. What would the slope be? Well, I hope that you'll see it's going to be the same, because it's -2 minus 1, which is -3. What about the slope here at -2, -1? Hopefully you can see that's going to be the same. See, the y value has no effect on this particular slope field, because there's no y value in this differential. This represents slopes. We're saying the slope, when x is -2 every time, it's going to be -3 every time. Hopefully you can see why that's the case. Now, are these slopes I'm drawing exactly -3? Absolutely not. It's definitely negative and it's definitely steep. To sum up all of this jazz I just wrote down there, when x is -2, the slope is going to be -3. What about when x is -1? Keep in mind we're leaving y out because there's no y in the differential. The slope is going to be -1 to -1, which is -2. It's still negative. It's still pretty steep, so maybe it looks more like this. That's going to be true for all of these. All of these meaning when x is -1. I know you can't copy and paste, but I'm just trying to make my graph as nice as I can. What about when x is 0? Slope's going to be 0 minus 1, which is -1. Still negative, but it's not as steep. I accidentally drew this longer than the other ones. That is just coincidence. That was not a plan. What about when x is 1? It's going to be y prime is 1 minus 1, which is 0. So that's horizontal, 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 horizontal. You know what that tells us? For every solution to this, which we said a general solution was 1/2 x squared minus x plus c, I believe. Since those slopes are all 0, no matter what c value I pick, the minimum is always going to be at x equals 1. That's what that tells us. What about when x equals 2? The slope is going to be 2 minus 1, which is a positive 1. So +1 slope for all of these. This represents a slope field. We have answered the question. Now, just to give you an idea of how this works, these aren't actual solutions. It's just an idea of how this works. Let's say that C was a +1. It's the y-intercept. Then maybe you would get this graph. See how that's a parabola? See how that works? Let's say that C was -1. Well, maybe the graph would look like this. See, those slopes represent slopes of tangent lines at those specific places. This represents all the solutions, and a blue one and that red one would be a particular solution. Let's try this again. This next one, it's talking about, notice that the segments drawn on the grid above would form parabolas, which we just talked about. They were connected. So now, given the differential equation below, compute the slope of each point and then indicate on the grid to the right. So I'm going to try to do this in a systematic way that is going to minimize the amount of work that I have to do. So this is saying the slope is equal to x minus y. So I'm going to focus right now on this diagonal. Not a great diagonal, but that diagonal right there. In each of those ordered pairs, x and y are the same value. So if x and y are the same value, if I subtract one from the other, I'm going to get 0. So just as an example, first of all, if x equals y, dy over dx is going to be 0. And just so you understand why that's true, let's say that we had the ordered pair 1, 1. We would have dy over dx equals 1 minus 1, which is 0. Anytime x and y are the same value, the slope's going to be 0. So I'm representing the slopes by drawing these segments that says, hey, the slope here was going to be 0. Let's see. if I continue on this next diagonal, say this one right here, it doesn't always work that you get these wonderful patterns, by the way. So in this case, let's take this point right here, 0, 1. So we're saying y is bigger than x by exactly 1. dy over dx, that's going to be 0 minus 1, which is negative 1. Every case on that diagonal I just drew, the y value is 1 more than the x value. So if that's the case, the slope's going to be negative 1 every time, and that's going to look something like this. If looking at these patterns doesn't work for you, then just calculate each of these slopes individually. I'm going to go to this diagonal. On this diagonal, if I pick a point like this one here, we can see the y value is 2 more than the x value. So just as an example, at 0, 2, the slope is x minus y, that's a negative 2. So on this diagonal, slopes are negative, and they are more steep than they were previously. Say something like this. Just try to make these slopes all the same. Difficult to do when you're doing it by hand. Do you notice the pattern? You went 0, negative 1, negative 2. This one's going to be negative 3. Which means this next diagonal is going to be negative 4. It's getting super steep. This next one's negative 5, which is getting real close to being vertical. If we come down here, following the pattern, negative 5, negative 4, negative 3, negative 2, negative 1, 0. This one's probably going to be a slope of 1. Let's just check to make sure. If I take this point right here, which is 0, negative 1, y prime is going to be 0 minus a negative 1, which is positive 1. Just what we expected. So that slope's 1. It's going to be the same on this entire diagonal because in each case, the x value is 1 bigger than the y value. Following this pattern, this slope should probably be 2. If you check the work, you will find that it is. It's more steep than the previous one. Try to make them similar. The next one, next diagonal is going to be negative 3, or positive 3, I should say. Hopefully I said positive 2 for the last one. And this one's going to be positive 4. All right, that represents that slope field. Let's check out this next problem. By the way, just to point this out, you can show as much or as little work as you want for this, but this should be pretty accurate. Accurate meaning, when they give you points for this, they're going to give you points for, did you get all the horizontal slopes correct? Then they might say, well, did you get everything in this quadrant up here? I'm using the word quadrant loosely. Are all these slopes negative? Are all these slopes positive? They're not going to get a ruler out and measure and see what your slope is. Shown below is a slope field for which of the following differential equations? Well, let's see. Now we could, it's a terrible idea, but we could separate the variables in each of these cases and then find the original function and see which of those looks like what this would look like. I don't recommend that. Let's see if we can notice some kind of a pattern with the numbers. For example, let me just pick a random ordered pair. Pick this one right here. Negative 1, 2. The slope at negative 1, 2 is 0. So if I put negative 1, 2 into this one, I would get negative 1 times 2, I would get negative 2. Well, this slope here is clearly 0, so that's not the answer. I am guessing and checking. That's how I'm doing this. If we get more than one answer, they get 0 here, then we'll pick another point. So here, if our x value is -1 and our y value is 2, this is going to give us a -4. That's not the answer. C at -1, 2. Take -1 times 2 plus 2. That does give me 0. Maybe that's the answer. For this next one, I'm going to have -1 times 2. I'm using this ordered pair again, seeing if this works. Plus -1. It's going to be -3. That did not work. And then this last one, if this is a 0, I'm not in the clear yet, but if it's not a 0, I'm in the clear. Take -1 plus 1. It's going to give me 0 cubed, which is 0. So maybe this answer works also. Well, let me check another point. So I need to compare C and E. This is C, and this is E. So let's say that I choose, so I don't want to choose a point on here again. So I think that's going to give me 0 for both of these. Let me pick, let's say, this point here, 2, 0. And let's see if we get a slope of 0. Here, if I put 2 in times 0 plus 0, I get a slope of 0. Here, if I do 2 plus 1 cubed, I do not get 0. So C is the only answer that works for the 2 different random points that I picked, and they weren't that random. I chose things that had a slope of 0 because that made it easier for me. Guess and check. That's what we did there. What I'd like you to do, well, let me give you some guidance first, and then I'll tell you what I'd like you to do for this. So at a certain point, I'm going to ask you to pause this video and you try to come to some conclusions on this. Since the slope represents all the particular solutions to a differential equation and the solution represents the antiderivative to a differential, then the slope field should take the shape of the antiderivative. Match the slope field for the differential equation on the next page. So what you'd want to do for these, you'd want to separate the variables and then find the antiderivative in each of these cases. So for example, this one here, we would get dy equals sine of x dx. If you integrate both sides, you're going to get y equals negative cosine of x plus your arbitrary constant. You want to do that for all 10 of these. Then if I look, is it obvious which of those graphs on the other side could be negative cosine of x plus an arbitrary constant? Well, definitely not this one. Definitely not this one. Definitely not this one. Maybe this one. Definitely not. Definitely not. Definitely not. I would say that it's D or I. Now, I'm going to come to a conclusion at some point, but I've narrowed that down to D or I because those are the only graphs here that look like trig functions. So like as another example, what does this one look like? Looks like a parabola. There's a bunch of parabolas hidden in this. This one here looks linear. So if any of my answers end up being a linear graph, it's probably going to be this one. So please pause this video, take a moment and find the antiderivative of each of these, and then try to, at the very minimum, narrow down to one or the other. And then hopefully you can come to a conclusion because each graph is going to match up with each of these. So let me walk you through the conclusions I came to. So when I did number 3 end up with this function, which is logarithmic. So I'm looking for a graph that resembles a logarithm, which I thought B was the only one that did that. 5, when I integrated this, I got a quartic function. I thought H was the only one that looked like it could have that kind of curvature. 7, this was a quadratic that opens down because the lead coefficient's negative, and I thought G was the only one that did that. 9 is a cubic function, looks like this, and C was the only one that I thought resembled a cubic function. And for number 2, you integrated it, you got a quadratic that opens up. F or A could be those answers. I'll get back in a moment why I chose A. 4, linear. The only graph that was linear was J. 6 is 2 times sine, so that could be D or I. Ultimately, I choose D for that. And 8 was another quadratic, opens up. Since this is a 1/2, it's going to open up slower, whereas the one above, A, coefficient's 1, it's going to open up quicker. In other words, skinnier, fatter. And then 10, this is a logarithmic function. Logarithms look like this, or it could look like this, or it could look like this, or it could look like this. Since this is negative natural log, that well, the only one that resembled a logarithm I thought was E. So let me take back what I just said about all that stuff. Logarithmic function looks like this. And this negative reflects it vertically, so it looks more like this. And I thought that E had those characteristics. So this is not an easy task, doing this, but you should be able to pick out things, at least parent graphs of what they resemble.